Welcome to the Deep Dive, where we take complex research and really break down the metrics that matter. Today, we are tackling a question that's just central to cognition and, frankly, to neurological health. If the critical communication lines in your brain start to fray, can the network around them just adapt? Can it mask the problem and, keep up the illusion that everything's running smoothly?
It's a really hopeful thought, isn't it? That the brain is so resilient it can just sort of paper over any failure. But what our sources for this dive reveal is something much more objective, almost ruthless in a way. When the physical structure that manages timing is damaged, the chaos that follows leaves this undeniable, measurable footprint. The system literally cannot lie.
Exactly. That's what we're calling the honest scale. We're diving into the biophysics that proves neural asynchronicity is just impossible to hide once that crucial protective layer, myelin, starts to fail. Our mission today is to really understand the precise metrics that measure this decay, this loss of temporal order, to see how a loss of insulation turns a crisp, coordinated signal into, well, chaotic noise.
And to do that, we're going to be looking at one of the most critical communication highways in the entire central nervous system. We're talking about the corticothalamic loop. This is, for all intents and purposes, the engine room for how you process sensory information and perform cognitive tasks.
Okay, let's unpack that circuit because I think understanding its job is fundamental to seeing the fallout when it fails. We're focusing on the layer 5 nerve cells, or L5 cells. They're located in the cerebral cortex. That's the wrinkly outer layer of your brain. It's the seat of all high-level thought, perception, decision-making. These are the source cells.
Right. And you can think of these L5 neurons as being like, middle management. They synthesize all this complex data coming in, and they have to decide what information needs to be communicated immediately. And they send these long-range signals down their axons, their communication lines, to a really deep, crucial staging area. It's called the posterior medial thalamus, or POM for short. And that connection from the L5 source to the POM destination, that's the corticothalamic loop.
And that loop is what translates sensation into perception.
Right. I know the research models this with mice exploring their world with their whiskers, and this loop processes that precise tactile input. But in humans, this exact same pathway is vital for much higher level stuff, like knowing where you are in a room, orienting yourself in a city, or even something as simple as recognizing a friend's face and recalling their name instantly. If that loop fails, all of those tasks just start to fall apart.
And the success of that loop, its speed, its reliability, it hinges almost entirely on the myelin sheath. Myelin is that fatty protective wrapping around the axons. And look, it's not just about making the signal go fast. That's what everyone thinks. It's about making it go consistently. It's about ensuring the signal always arrives at the same time with extreme temporal fidelity.
We hear about myelin a lot, but what makes the myelin on these specific L5 cells so uniquely critical? Is it just standard insulation, or is there something special happening right at the start of the line? Well, the sources really highlight a unique structural imperative right at the signal's origin. In these specific L5 cells, the very first part of the axon, right where the cell body makes the decision to fire, it's called the axon initial segment, or AIS. And it's isolated in a very, very particular way. This initial wrapping, this specific structure, is like the starting pistol for the entire system. It is absolutely essential for dictating that fast and, crucially, that consistent timing of the signal all the way down the line. It sets the rhythm.
So it's like the first Lego block in the chain. If that specialized myelin wrapping is the most critical starting point, what happens when it gets compromised? How did the researchers even introduce the failure?
They needed a really precise model of demyelination. So what the researchers did was administer a toxic substance called cuprazone or Kupzi mice over a period of 6 weeks. This chemical is a pretty standard method for inducing demyelination across the central nervous system.
And this is where the specificity of this study becomes so important, right? Because most of the historical studies of demyelination, they focused on the big white matter tracks, the long cables connecting distant brain regions. But the damage here was really geographically focused.
Absolutely. The unique power of this model is that the damage was concentrated precisely in the L5 and L6 layers of the cortex. These are what are known as gray matter lesions, and that's really distinct from the widespread damage you might find in, say, the white matter.
Why focus on gray matter lesions? I mean, as a listener, I would assume that damaging the big long-distance highways, the white matter, would be the biggest problem. Why zero in on the source of the signal in the cortex?
That is a critical question. And while, yes, damage to white matter tracts absolutely causes issues, severe forms of neurodegenerative diseases like multiple sclerosis or MS, the ones associated with extensive gray matter lesions, they tend to correlate with significantly worse, more profound cognitive outcomes. We're talking about the deep, life-altering symptoms, disorientation, failures in executive function, major memory recall issues.
So by concentrating the damage right at the L5 signal source, in the cortical gray matter, they are basically modeling the fundamental biophysical cause of the most severe cognitive breakdowns we see in MS patients.
Precisely. The sources were very careful to confirm that the myelin damage did not significantly affect the white matter tracts leading out of the cortex, nor did it damage the posterior thalamus, the POM itself. So this isolates the problem beautifully. It allows them to study what happens when the signal creation is flawed, not just the long-distance cable, and then they can just watch the inevitable ripple effect through the whole circuit.
So the stage is set. We've got a damaged starting point, the myelin sheath around these cortical L5 neurons. And now we're watching the entire communication loop to see if the system can hide this failure. If the L5 neurons try to compensate, will the POM still get the message cleanly? And the biophysical evidence seems to suggest that, well, compensation is impossible.
The underlying physics of cellular communication are absolute. The system has no choice but to reveal the dysfunction.
Okay, let's look at that first undeniable metric, what we're calling signal corruption, the broken scale. If you step on a scale, it tells you your weight. It's objective. It doesn't care how you feel about it. In the same way, when an action potential travels down a compromised axon, the physics of conduction objectively reveal time corruption.
Yes, the key role of myelin is temporal order. It's all about timing. It ensures that these discrete electrical signals, these action potentials, they travel not only quickly but consistently. When you lose that consistency because of demyelination, the signal transmission is no longer a clear, synchronized musical chord. It just becomes a sloppy, staggered cacophony.
So how did the researchers quantify this corruption of time? What were the raw measurements?
They measured the signal transmission time from the L5 neurons all the way to the POM cells. And the demyelinated axons showed two immediate catastrophic failures in temporal fidelity. First, there's a measurable and significant increase in delay from the L5 cell spiking to the POM cell spiking. The signal simply took longer to get where it was going.
Okay, so the overall commute time went up. What was the second failure, the one that really destroys the order of operations?
The second was the dramatic increase in jitter. Jitter is just the variance in the spike arrival timing. So if we use an analogy of a synchronized corporate team, right? They need to submit reports at exactly 10:00 a.m. every day. A healthy myelinated system delivers the report at 10:00:01 a.m. consistently. Every single time. An asynchronous demyelinated system, well, it delivers it at 10:00:00:000.50 a.m. the next, then 10:00:0.000.000. That variance, that jitter, it corrupts the entire sequence. It proves that the temporal order is just destroyed.
And this brings us straight to that brilliant analogy from Professor Martin Kole's team, the barcode failure. I think this is the perfect visualization for you, our listener, to latch onto.
It's excellent because it focuses on the information loss, not just the speed. A healthy neural burst, which is a quick series of high-frequency action potentials, is like a barcode. That barcode is a precise sequence of information that's needed for identification. And the POM, the receiving station, it's the scanner. It needs the full code in the correct sequence and timing to register the input correctly.
And if the myelin right at the start of the axon is damaged?
This team says you are effectively skipping the first black stripe of the barcode. When that first piece of insulation is compromised, the very first action potential in that burst is often lost completely, or it's severely delayed. So this isn't just a slower signal. It's a missing piece of fundamental data that renders the whole product, the whole message, completely unrecognizable.
Let's put some numbers on that reliability hit, because the data is just striking. How reliable is a healthy system compared to this compromised one?
Well, the whole efficiency of these circuits relies on these high-frequency, reliable bursts of information. In a healthy, synchronous L5 to POM system, the probability of the first spike in that burst successfully reaching its target in the POM is incredibly high. We're talking, it often approaches 90%. That's a highly reliable communication channel.
And what happens in the demyelinated model?
In the asynchronous demyelinated system, that crucial first spike probability drops. It drops significantly. It often trends down towards 70% reliability. And on top of that, the overall average number of spikes that are actually received by the POM is reduced. So the source cell might be firing robustly, but the message is literally decaying mid-flight. The integrity is just gone.
Wait, I want to linger on that for a second. The magnitude of that first spike failure. If the system is sending a burst of information in the whole series of spikes, why is the first one so uniquely important? I mean, why can't the POM just use the spikes that come after it?
Because that first spike often serves as the temporal anchor. It marks the absolute beginning of the event. It says, start now. If you miss that initial anchor, the subsequent spikes just arrive as this disorganized stream, and they lack a cohesive starting time. It's like trying to coordinate an orchestra where the conductor's downbeat is only audible 7 out of 10 times. And even when it is audible, it's jittered by several seconds. You simply can't build a symphony or a coherent perception of reality on that kind of fundamental timing failure.
So if the system can no longer reliably distinguish now from later, what's the overall functional impact on the organism?
It leads to what we could call the breaking of the brain's arrow of time. The physicist Richard Feynman once defined time as simply the ordering of events. Myelin loss destroys that ordering principle for sensory events. The mouse in the study can feel something with its whiskers, but the timing is so chaotic the brain can't synchronize all the converging inputs to definitively register what the object is, or where it is, or when the action happened.
It's the ultimate loss of a grip on reality, and it's just from sheer temporal entropy. The system gets the sensory input, but because the timing is so fragmented and corrupted, that input becomes functionally unrecognizable to the animal.
And critically, the researchers showed this was an inherent defect in the axon's ability to conduct the signal. It wasn't a flaw in the neuron's ability to initiate the signal. They used optogenetics, light-activated stimulation, and they showed that even with a strong high-power stimulus, the control neurons fired with precision. But the coprazone neurons, the demyelinated ones, still showed that increased delay and jitter. The broken scale of time is a physical consequence of the demyelination. You just can't get around it.
Okay, so the signal corruption is measurable, it's specific, and it's directly linked to that frayed insulation. That brings us perfectly to metric number 2. If the message is getting corrupted in transit, what is the metabolic cost of the source neuron trying to fix the problem? Let's talk about compensatory hyperactivity, the sweating neuron.
This is where we see the biological system trying desperately to hide its own failure. If the L5 neuron senses that its signals are decaying or failing to propagate reliably, which they are, it enters a state of panic. It tries to shout over the noise by increasing its output dramatically.
And this shouting is something you can actually quantify through these sophisticated computational models that mimic the real action potential bursts. What do those simulations show about the source neuron's panic response?
The simulations, which were constrained by the actual experimental data, clearly showed that the demyelinated L5 neurons became severely hyperexcitable. They started initiating bursts at significantly higher intraburst frequencies. They were just pushing out signals much faster than the system was ever designed for.
Let's get granular on that. You say they're screaming. What were the heart numbers?
In the control model, the healthy L5 neuron produced its action potential bursts at a robust but efficient frequency of about 190.4 hertz. So 190 hertz, that's its normal operating volume. But the demyelinated model neuron, it jacked that frequency up significantly, forcing bursts out at approximately 219.4 hertz.
Wow, that's a substantial increase. I mean, biologically, that's a huge jump in frequency. It's like turning the volume knob up 20% and just trying to scream across a broken telephone line.
Yeah.
That must require an immense amount of metabolic energy just to start the transmission.
Exactly. The neuron is basically attempting to increase the probability that at least one of its signals will manage to penetrate the noise and reach the POM. But here is the central tragic paradox of this whole dysfunction. The high cost is met with a devastatingly low return.
Right, the physical footprint of the dysfunction is this massive discrepancy.
Yeah.
Tell us about the failure rate.
So despite the L5 neuron generating these powerful high-frequency signals at the soma, at the cell body, the propagation along that demyelinated axon fails dramatically. The researchers found nearly a 5-fold increase in the failure rate for individual action potentials within that high-frequency burst.
A 5-fold increase. That sounds like a catastrophic breakdown.
It is. The control axon model operating efficiently at 190 hertz, it only failed about 6% of the time. which is pretty good. But the demyelinated model, screaming at 219 hertz, saw its failure rate skyrocket to approximately 32%.
So 1/3 of the message is failing to propagate, even as the neuron is expending 20% more energy trying to send it. That is a classic example of inefficiency being masked by brute force, which in the end just drains the whole system.
And the analysis located this failure point with precision. It occurred specifically beyond the axon initial segment, that trigger zone. And critically, it happened around the very first node of Ranvier. The node is the gap in the myelin sheath that acts as a signal booster. If the insulation before that first booster is frayed, the signal just leaks out right before it can be amplified.
Let's use our Lego analogy here for a second for anyone thinking visually. If the healthy neuron is a sophisticated Lego Technic mechanism where every piece connects perfectly,
Yeah.
then the AIS is the motor, the nodes of Ranvier are the strategically placed gear assemblies, and the myelin is the specialized tight-fitting connectors that hold the whole structure rigidly in place.
Yes, that's perfect. And when the myelin connectors are lost near that first gear assembly, near that first node, the signal, the mechanical motion, it just wobbles and decays right at the start. The motor, the L5 soma, detects this decay and it compensates by spinning faster. It goes up to 219 hertz. But because the physical connections are compromised, that extra energy just results in the structure flying apart. That's the 32% failure rate. It's all high effort, pure waste.
This hyperexcitability also leads to some fascinating and really problematic microscopic changes.
Right.
With calcium and sodium signaling, this is where the sweating neuron becomes a chemical reality.
Indeed. We know the AIS and the nodes of Ranvier are just densely packed with voltage-gated sodium channels. They're the electrical power source. But the research points out that these sodium channels aren't perfect. They aren't just for sodium. They're also a route for a significant rapid influx of calcium. It's called ICANA. And this happens over submillisecond timescales.
So the electrical mechanism, the sodium channels, also has this chemical side effect, this calcium influx.
Correct. And this intense compartmentalized calcium signaling is highly localized to these sodium-rich areas. On top of that, the L5 neurons have these highly localized internal calcium storage units, like the specialized smooth endoplasmic reticulum, which is known as the giant saccular organelle, and it's located right in the AIS. This organelle is there to amplify and manage calcium signals.
That sounds incredibly important for fast, localized control. So how does demyelination exploit this precise mechanism?
Well, when the myelin insulation is lost, the previously protected membrane is now exposed. The neuron has to rely more and more on these high-density sodium channel domains just to push the signal through. And this exposed, highly excitable membrane, it's constantly being fueled by this rapid calcium signaling from both the sodium channels and those internal stores, like that giant saccular organelle. And all of that contributes to the hyperexcitability we measured.
And the chemical consequence of all that exposure and intense activity.
The energy and the calcium overload start to drive the generation of spontaneous localized spikes that originate in the axon itself. They aren't being triggered by the cell body's decision. These are called ectopic action potentials.
Ectopic spikes, they are essentially noise, aren't they? They're signals generated by a panicked, chemically stressed membrane. I really like the term biological eyes for them.
They are exactly that. The source neuron is so distressed trying to compensate firing at 219 hertz that the exposed calcium-fueled membrane starts generating its own extraneous static. So the system is simultaneously failing to transmit its intended signal 32% failure rate while also generating false signals, these lies, that just confuse the entire network. The sweating neuron cannot hide its metabolic and its informational distress.
So we've tracked the signal from source to failure, and we've measured the source's hyperactive response. Now, what about the destination? That brings us perfectly to the final, unavoidable metric, structural and functional reorganization. Or, as we're calling it, the system's lowered standard. The receiving end, the POM, has to adapt to receiving these unreliable, jittered signals.
Right. When the receiving station realizes the source material is chaotic, it really only has two choices: stop processing anything at all, or lower its precision standards to try and glean some kind of utility from the mess. And the POM chooses the latter. And we can measure that change.
Okay, so let's look at the POM's job in a healthy system first. What's its standard operating procedure?
The POM is a specialized filter. It's known as a coincidence detector. You can think of it like a very strict quality control checkpoint. It doesn't just register that a signal arrived. It requires signals from multiple converging inputs, say input A and input B, to arrive within a very narrow, very strict temporal integration window. We're usually talking about only a few milliseconds wide.
So it's a Boolean A and D gate. A and B must arrive right now for the information to be integrated. Precision is the non-negotiable requirement.
Precisely. But when the asynchronous chaos hits, when signals are significantly delayed and they arrive with massive jitter, the PM can no longer fulfill this job under its normal, strict standards. If every incoming event is staggered and late, its job of comparing and integrating inputs becomes functionally impossible.
How did the researchers visually demonstrate that the PM had lowered its standards?
They looked at the timing of the PM's electrical response peaks after optogenetically stimulating the L5 axons. In the control neurons, the healthy PM showed two distinct, precise peaks of response. We saw an early processing peak at about 6.8 milliseconds, and then a distinct later peak at 17.7 milliseconds.
And those two peaks, they likely represent two different, temporally separated but still synchronized input pathways that are converging on the thalamus. Two clear processing windows.
Correct. But now look at the demyelinated neurons. These two sharp, distinct temporal moments just collapsed. Instead of two clear time slots, the researchers observed a single, broad, late peak that occurred at about 19.03 milliseconds.
That is powerful. It's undeniable evidence of a functional failure. The PMO has lost its ability to temporally differentiate inputs. It's moved from precision multitasking processing A at 6.8 and B at 17.7 to this chaotic single-stream processing. It's just registering everything as a single disorganized late blob.
The system is sacrificing fidelity for function. The PUM is forced to widen its acceptance gate, its temporal integration window, to just acknowledge that something arrived, even though it can't distinguish when or what exactly arrived in the sequence. It is the very definition of a lowered standard.
Now, we have to be sure to connect this back to the initial setup. Did the POM itself sustain damage and become inherently dysfunctional? Or is this lowered standard purely a reaction to the corrupted input it's receiving?
The sources are extremely helpful here in localizing the fault. The researchers explicitly ruled out damage to the POM. They confirmed the intrinsic membrane properties of the POM neurons were completely unchanged. The receiving hardware was still functional.
And what about the actual connection points, the synapses?
Even the L5 to POM synaptic properties, things like the maximum signal amplitude, how fast the synapse adapted to frequency, even the size of the massive terminal structures called giant boutons, all of them were unchanged after the cortisone treatment.
So the fault lies strictly with the signal transit and the source's own hyperexcitability. The receiving station is physically fine, but the data stream is so compromised it's forced to adapt its entire processing window.
Exactly. And the structural evidence confirms where the problem lies. The sources confirmed that the physical structures along the L5 axon itself were compromised. The internode length, that's the insulated sections between the nodes of Ranvier, it decreased.
The insulation segments got shorter. The cables are literally fraying.
And crucially, they measured a significant reduction in the density of a protein called Caspr in the cortex. Caspr is a critical protein marker that literally anchors the myelin sheath tightly to the axon at the perinodal regions, right next to the nodes of Ranvier.
And that structural compromise is the physical evidence of the honest scale in action. Reduced Caspr means the myelin is physically detaching, which leads directly to that failure of long-range action potential propagation that causes all the jitter and delay in the first place.
It connects everything. The physical compromise of the sheath leads to the temporal corruption, which is metric 1, that forces the source into a metabolic panic, metric 2. Which in turn forces the receiver to abandon all precision, which is metric 3.
Let's step back and consider our Lego analogy again, but this time from the receiving end. If the PM is trying to build a complex sensory model, let's say a specific Lego castle, it needs input A, the wall section, to arrive at 6.8 milliseconds. And it needs input B, the turret section, to arrive at 17.7 milliseconds. If the source sends them both late, jittered, and partially broken, what does the PM do?
Well, it can't reject the parts entirely because then the cognitive task just fails completely. So it's forced to say, okay, I will take all incoming parts that arrive between, say, 15 and 25 milliseconds, and I will just assemble them as best I can into a single, less refined piece. And the resulting cognitive experience is based on this poorly timed wide window integration, which is why people struggle to recall familiar names or orient themselves. The model is just mushy.
So the ultimate implication is that the brain, when faced with this structural failure, is forced to sacrifice temporal fidelity, the very currency of information processing, just for mere existence. It gives up precision just to keep the lights on.
And as the researchers note, this reduction in fidelity is what causes the brain to lose its grip on reality. It turns a precise, integrated timeline into a chaotic sequence of disordered subjective events. This is why conditions that are tied to gray matter demyelination often lead to these severe, debilitating cognitive impairments.
This deep dive has really shown that there is absolutely no hiding when myelin fails. The biophysical metrics provide three undeniable footprints of this asynchronicity. It all proves the integrity of that honest scale.
First, the system reveals the failure through signal corruption, the barcode failure. We can measure the increased delay and jitter, and that collapse of reliability in the essential first spike of a burst, with the probability dropping from, high efficiency down towards 70%. The timing of now is immediately destabilized.
Second, the source reveals its distress through compensatory hyperactivity, the sweating neuron. It panics.
Yeah.
It turns up its output frequency significantly, from about 190 hertz to 219 hertz in the models, which tragically just generates a metabolic cost that simultaneously causes a massive propagation failure, jumping from 6% to 32% failure within the burst. That high-cost, low-return effort is the quantifiable signature of the system's metabolic distress.
And third, the receiving system reveals the failure through structural and functional reorganization. The lowered standard, the PM, that once strict coincidence detector, can no longer distinguish between rapid inputs. And you see it in the data, the collapse of two precise timing peaks, 6.8 and 17.7 milliseconds, into one chaotic late broad peak at 19 milliseconds.
And all of this biophysical chaos is directly linked back to the physical compromise of the axon structure itself. It's proven by that reduced Casper density and the decreased internode length in the cortex, confirming the problem lies precisely in the wiring insulation, not in the receiving hub.
Without the temporal synchronicity that myelin assures, the brain struggles profoundly. If you can't trust when a message arrives, you can't trust the message itself. And that is the basis for the severe cognitive symptoms we see in clinical conditions associated with these gray matter lesions.
Which raises the ultimate question for research moving forward. The study authors, particularly Professor Kole's team, are already investigating how damaged myelin could potentially be recovered or repaired. And that's the massive therapeutic frontier for MS. But if we think about the fundamental problem just being the lack of temporal fidelity.
And we know that precise timing is essential for coordinating neural network oscillations, like the critical gamma frequency that so often falls apart in these conditions.
And we also know from other related research that external interventions, like delivering precise gamma frequency stimulation around 40 hertz, are being explored for their potential to activate glia and improve cognitive symptoms.
Then the technological and the biological frontier becomes pretty clear. If the physical insulation is gone, and the biological system can no longer achieve temporal synchronicity on its own, if that neuron is just hopelessly stuck screaming at 219 hertz with the 32% failure rate, can we use non-biological external tools to essentially force the circuit back into temporal order? Can we impose synchronization from the outside, overriding the need for perfect myelin? And what would that mean for restoring cognitive function and giving a patient back their grip on reality?
Can we force the entire chaotic Lego structure to just click into place at 40 hertz, even if the individual connectors are frayed and broken? That's a profound question about the future of cognitive restoration, and one we will leave you with to chew on. Thank you for diving deep with us. We'll see you next time.